Okay, now it is time. So, good evening, dear participants of our school. Thank you for coming. And it is my pleasure again to announce Zakhar, his second lecture. So, Zakhar, please.
Yes, thank you very much. In this lecture, I will be talking about conic intrinsic volumes, but we have to start with the definition of the, or by recalling what are the usual intrinsic volumes. So the usual intrinsic volumes are defined for polytopes, or more generally for convex bodies, and the conic intrinsic volumes are defined for cones. So as I start by defining the usual intrinsic volumes, and I will define them only for polytopes. So let P be a polytope in dimension D. Let BD be the unit ball in the D-dimensional space. And let kappa D be the volume of this unit ball. Or maybe like this. And a formula for it is known. It is pi to the power D half divided by D half factorial, where if this is non-integer, it has to be understood as a gamma function. And P is a polytope. And now there are many ways to define the intrinsic volumes, and one of the ways is via the Steiner.
Sorry, maybe it is D plus 1 or D over 2
gamma
plus
of
1.
D, you mean gamma of D?
Oh, sorry, it's factorial. Yeah, sorry.
Maybe it's wrong. Yes. I hope.
No, it's right. I didn't see factorial. I saw it's gamma. Yes.
Okay. So we consider the Minkowski sum of the polytope plus a ball of radius BD, which is the set of all x in Rd, which have a distance less or equal to r to this polytope P. So in dimension 2, it looks as follows. If we have a polygon, something like this, then we consider a neighborhood of this polygon of size r. So all points which have distance at most r to this polygon P. This is P, and the neighborhood looks as follows. And now the Steiner formula gives the volume of this neighborhood, P plus R times BD. For example, in dimension 2, we can do the following. We can say that the area of this neighborhood is just the area of P. So it is that, plus the area of all these rectangles, which can be computed by taking the perimeter of P and multiplying it by R, and plus the area of all these sectors. But it's easy to see that if we put them together, they form just one disk of radius R. So one has here pi R squared. So the Steiner formula says that the volume of this neighborhood is a polynomial in R of degree 2 in this case, and in general it is a polynomial of degree D. So let us state this formula for general D. The volume, or maybe let us derive it. So we have now a polytope of a general dimension D, and then it is easy to see that the neighborhood of this polytope consists of contributions of various phases, namely its phase, each phase, f of dimension I of P, contributes the following term. By this I mean the following. For example, if we take here in the two-dimensional case this face, this side, then this is the contribution of this side, right? And in general, we can see, for example, the following. To give another example, let us consider something in dimension 3, something like this. I'm sorry. Something like this. And the contribution, so this is a part of a polytope, and this, and I would like to consider the contribution of this phase. And it looks as follows. It contributes the following domain, something like this. Right? I hope you understand what I mean by the contribution of a phase. It's this figure, and its volume is given by the following formula. First of all, we have to take the volume of the phase, the volume in the I-dimensional sense. So in this case, it's just the length of this. Then we have to multiply it by r to the power d minus I, because it is the complementary dimension. And I would like to multiply it by the volume of the ball in dimension d minus I. So if we would have here the full ball, then that term would be its volume. But we don't have the full ball. So if we would have such a cylinder, right, then so this would be the volume of the cylinder, namely this h multiplied directly by this ball. But we don't have the full ball, we have just some piece of it. And therefore, we have to multiply it by the gamma of Fp, which is the external angle of F in the polytope P. I will define it right now. So this is the external angle, or I will define it a little bit later. But now we see that the contribution of phase F is given by this formula, and in order to obtain the volume of the whole neighborhood, we have to sum up all the contributions. So the volume of the neighborhood is given by the sum, and I will take the sum over all dimensions, I equals to 0 from 0 to d. And then we take the sum over all phases of dimension I, and we see that this term is the same everywhere. So it is r to the power d minus I kappa d minus I. And then we have the sum over all f of these terms. And it is denoted by Vi and is called the case conic intrinsic, the case usual intrinsic volume. So where Vi of P is the sum over all f of dimension I, over all phases of dimension I, of the following terms: the volume of the phase times the external angle at this phase. And this is called the ith intrinsic volume. And now one can generalize the Steiner formula to any convex body. And it says then that the neighborhood of the volume of the R neighborhood of any convex body is given by a polynomial in R. And the coefficients of this polynomial are essentially the intrinsic volumes. So for example, the dth intrinsic volume, so V d of P is just the volume of d of P. It's the first term in this polynomial, or it's the last term in this polynomial. Then V d minus 1 of P can be obtained by taking all facets of P, so all phases of maximal dimension, and multiplying them by the angles, but all the external angles are 1/2 there, so it is 1/2 times the surface area of P, and so on. But we shall not need this, and in particular, we shall not need the Steiner formula, because we will define the conic intrinsic volumes in a different way. So there are many equivalent definitions of conic intrinsic volumes, and here is maybe the most simple one. Conic intrinsic volumes. First of all, these are defined for cones, and here is the definition of a cone. A cone for this talk is an intersection of finitely many half spaces so whose boundaries pass through the origin. So a cone C is an intersection of half spaces hi plus I from 1 to some number m, where hi half plus are subspaces such that they are bound in hyperplanes contain the origin. So in dimension 2, it's just something like an angle. Here is the origin, and this is a cone. And in general, this is usually called polyhedral cone, because there is a more general notion, but for this talk, we will just consider such polyhedral cones. Now, some examples. So in the plane, it is an angle. In general, there are trivial examples. For example, 0 is an example. RD is an example. Linear spaces are examples. Or, for example, the orthant. RD plus, which is the set of all points x, such that all coordinates are non-negative for all I. Something like this. And in general, a cone is just a set of solutions to a finite system of homogeneous linear inequalities. Homogeneous means that on the right-hand side we have 0. So it's a set of solutions to a finite system of homogeneous linear inequalities. One more example, the Weil chamber, which we shall see later in this talk. It's the cone given by the following system of inequalities. x1, the coordinates of the point, are decreasing. It's a Weil chamber of type A, for example. Now, given a cone, we define the metric projection on this cone. So let.
Sorry, and also they are positive, right? The coordinates.
If this is of type A, they are arbitrary, and if it is of type B, they are positive.
Ah, okay, so, okay, sorry. Yeah.
Both are Weil chambers. Now let's see be a cone, a polyhedral cone, and for x, a d-dimensional point, we define the notion of metric projection to the cone as follows. Pi c of x is the best approximation to x in C. So it is the minimizer of the distance from x to y over all y in C. So we try to approximate x by a point from C, and the best approximator is called the metric projection. For example, if the cone C is a linear space, then this is just the usual orthogonal projection. And now we can define the conic intrinsic volumes. So, definition. Let us first draw a picture here. Suppose we have a cone like this, and then there are some points which need not be projected at all. For example, if I take a point inside the cone itself, so this is C, then its projection is the point itself. So these points project to themselves. But there are some points which are projected to this face, this one, namely all points which are here. So all points here, if this is x, then this is the projection, right? And all these points which are here project to this face, to F1. Now, if this is F2, then there are also points which are projected to F2, namely these ones. And finally, there are also points which are projected to this vertex. All points which are here. So if this is x, it is projected to 0. So there are many possibilities for a point. It can be projected to a face of some dimension. And now the conic intrinsic volumes are defined as follows. So for k equals 0 and so on d, the k's intrinsic volume of C is the probability that the metric projection of a Gaussian random point in Rd is in the relative interior of some k-dimensional face of C. So here in this definition, G is standard Gaussian random point or random vector in Rd. Or if you like, it is any rotationally in any random vector with a rotationally invariant distribution. For example, you may take also uniform on the sphere, if you like it more. So we take here a random point on the sphere, and we look at the projection of this point. For example, if this point is here, or random point in the ball, you may take uniform distribution on the ball as well, BD. So we take a random point in the ball, and for example, if it is here, then it is projected to a face of dimension 2, and all these points contribute to the second conic intrinsic volume. For example, if the point is somewhere here or here, then it is projected to a face or to a relative interior of a face of dimension 1. So these contribute to dimension 1, and so on. So this was the contribution of dimension 2. That was the contribution of dimension 1, and this is contribution to the 0th conic intrinsic volume. Now, from this definition, it is immediately clear, and this is an important fact, that the sum of all conic intrinsic volumes is equal to 1, okay, from 0 to d, because any point is projected to a face or to a relative interior of a face of some dimension. So for some dimension, a point is projected to a face of this dimension, and therefore they sum up to 1. And also they are non-negative. So they are non-negative, which means that they form a probability distribution, all these numbers. Now, so they form a probability distribution. Now let us consider some simple examples. First, let us look at dimension 2. In dimension 2, we have just some angle, like here on this picture, and we have already argued that the second intrinsic volume of C is just the angle itself, measured such that the full solid angle is 1. So if alpha is this angle, then this is the second intrinsic volume. Well, what is the first intrinsic volume, or conic intrinsic volume? It is the probability that our point, uniformly distributed on a ball or on a sphere, is either in that domain or in that domain, but these are two right angles, and they sum up to half of a full solid angle, so it is 1/2 always. And finally, the 0th intrinsic volume is just the rest, because the sum should be 1, so it is 1/2 minus alpha. And now another example. Suppose that C is a linear space of dimension, say, j. What is then the conic, or what are then the conic intrinsic volumes? Okay, then the metric projection is just the usual orthogonal projection, and all points project to a face of dimension j in that sense, in that case, because C has dimension j. So the jth intrinsic volume is 1, and all other are 0 for all k not equal to j. So it's a sort of delta distribution. Subspaces, if we view the sequence of intrinsic volumes as a distribution, then the linear subspaces correspond to the delta distribution. Now, an example which is a little bit less trivial. Example, let C be the orthant. So the set of points where all coordinates are non-negative. Let us compute the intrinsic volumes, and to this end, we have to describe the metric projection. So let us take some point, let's say, for example, something like 1, -2, +2, -3, -1, 0, 1. What is the metric projection of this point to the orthant? Well, recall that the orthant consists of all points whose coordinates are non-negative. And so I want to approximate this point by a point with non-negative coordinates. Now, if some coordinate here is positive, I don't need to change it. But if some coordinate is negative, I have to change it by 0. That's the rule. So this point is mapped by the metric projection to the point 1, 0, 2, 0, 0, 0, 1. And this point is in a face of what dimension? Is in a relative interior of a face of what dimension? Recall that relative interior means it is in this face, but it is not in a face of smaller dimension. Okay, so I can consider the following face of the orthant. I can consider the face in which these coordinates at these 3 places are arbitrary, non-negative, of course, and the other coordinates are fixed to 0. So these coordinates, these ones are free, non-negative, and all the other are 0. This is a face of dimension 3. So the dimension of this face is 3. So this point is projected to a face of dimension 3. I hope it's more or less clear. I don't know. And now we want to compute the probability that a random point, say a random Gaussian vector, is projected to a face of dimension, say, 3. And what does it mean that this projection projected to a face of dimension 3? This means that it has 3 positive coordinates, like here. So the number of positive coordinates should be 3. And more generally, if we want to compute the probability that a point is projected to a face of dimension k, this is the same as the probability that k coordinates are greater than 0. But if we take a Gaussian vector, then all coordinates are independent and each coordinate is greater than 0 with probability 1/2. So it is binomial distribution. And we have at the end 1 over 2 to the power d times d over k. So the sequence of intrinsic volumes in this case forms a binomial distribution with parameters, I'm sorry, parameters d and 1/2 for the orthant. Now I'm going to introduce a formula or a way to compute these intrinsic volumes, which is somewhat similar to the definition of the usual intrinsic volumes, which was given here. So I want to find a conic analog of this formula, which will be useful later. And to this end, we need to introduce the important concept of duality for cones. So duality of cones. Recall that a cone is a set of solutions to a finite system of linear homogeneous inequalities. For example, I can write it as follows. So here is a cone. Cone C is a set of all x in Rd such that the scalar product of x with yi is smaller than 0. Let us write smaller for all I. And here y1 and so on ym in Rd, well, without 0 maybe, are the inequalities, so to say, which are satisfied by the points of this cone. So a cone is a set of points satisfying inequalities, and the dual cone is defined as the set of inequalities satisfied by the cone. So the dual cone is the set of all inequalities, which I denote by y, such that all points from C satisfy these inequalities. So x, y should be smaller than 0 for all x in C. So for example, y1, ym are in this dual cone. But also all positive combinations of y1, ym are in the dual cone. And in fact, the dual cone is given by a set of such positive combinations. Now, a remark. The dual of the dual is the cone itself. Some simple special cases. So the dual of 0 is Rd. The dual of a linear subspace L is just the orthogonal complement. If L is linear subspace. Something more complicated. What is the dual of the orthant, of the positive orthant? RD plus dual. So here is it. What is the dual? The dual is the set of all vectors such that the scalar products are negative with any vector with positive coordinates. So these are just vectors with negative coordinates. And we can write it as minus RD plus. So it's the negative orthant. This is RD plus, and this is the dual. What is the dual of the half space? A half space is also a cone. So what is the dual of the half space? What do you say? So any opinion? So it's a set of vectors such that any scalar product with any vector from this half space is negative or non-positive. And which vectors have this property? So for example, this vector, does it has this property? Okay. Is the scalar product always negative with any vector from the half space? Well, evidently not, yes, because I can take this one, and here the angle is less than 90 degrees, so the scalar product would be positive, right? And this argument applies to any vector except of this one. So this one has negative scalar product with any vector from the half space, right? Because all these angles are at least 90 degrees. So these vectors, this half line, right? This is the dual cone. So if this is our cone, this C, the half space, then the dual cone is this half line. Okay. And now to derive a formula for the conic intrinsic volumes, we can observe the following things. So for example, if we have a point which has to be projected, let's say in this example with the angle, if we want that a point is projected to 0, then it should be in the dual cone, because this is the dual cone here. So a point is projected to 0 if it is in the dual cone. And in order to describe all points which are projected to a given face, we have to introduce the concept of duality between the faces of the cone C and the dual cone C. Namely, we have the following. So first of all, I have to change the page. Namely, we have the following duality between the faces of C and the faces of the dual cone. So by ejection, k-dimensional faces of C are in one-to-one correspondence with d minus k-dimensional faces of C prime. Namely, let me again consider this example, because this is the only example one can draw in a nice way. So this is C and this is C dual. And now to any face of C, say to this one, I can do the following construction. I can construct the orthogonal complement of this space, which is a linear subspace, and take the intersection of this orthogonal complement with C dual. And then we get this face. And this is the dual face. So these two faces are said to be in duality. Namely, we can map each k-dimensional face of C to the following face of C dual. We take the linear hull of F, take its orthogonal complement, which is a linear space, and then we intersect it with C dual. The claim is that this is a face of C dual, which is maybe not so easy to prove, but I hope it's easy to believe. And it has dimension d minus k because we have taken here the orthogonal complement. So this was k-dimensional, the linear hull is k-dimensional, and this is d minus k-dimensional. And this is a face of C dual. And it is denoted by n of f c and it is called the normal phase of F. So for example, if this is F, then this is the normal phase of F. If this is F, then this is the normal phase. Now, what is the normal phase, say, of 0? 0 is also a phase, the zero-dimensional phase of C. What is the normal phase of 0? Okay, what is the orthogonal complement of 0? It is the whole space, right? The whole plane in this case, and then I have to intersect it with C dual. So it is, in this case, it is C dual. So the zero-dimensional phase 0 corresponds to the two-dimensional phase C dual, and vice versa. The two-dimensional phase C here, so all of this corresponds to the 0 in the dual cone. So they are
Zakhar,
yes.
Zakhar, I'm afraid many people know, but are too shy to answer. Sorry.
Okay. Yes, I hope so. And now, given this duality, we can give a formula for the conic intrinsic volume, so an explicit formula. The case conic intrinsic volume of C is what? Okay, it is the probability, recall, it is the probability that a uniformly chosen random point projects to a k-dimensional phase. So I have to take the sum of all k-dimensional phases. And then let us describe all the points which are projected to the relative interior of F. And to this end, let me try to draw a picture in dimension 4. So suppose this is F, it is two-dimensional. And there is an orthogonal complement of F, which is also two-dimensional. And there is a dual phase. So this is the normal phase. It is here. And now, which points project to, in R4, which points project to this phase F? So X projects to the relative interior of F if and only if X is where? Well, it should be above F in the direction of this dual phase, right? So it should be in F direct orthogonal sum with the normal phase, right? I think this is more or less, well, maybe it's not it's of course not a proof what I give here, but I think it should be easy to believe. Now, and now what is the probability that X is here? So X should be in this orthogonal direct sum, and what is the probability? Well, the probability that we have here X, right? And we have two projections. We can decompose the point X into two components which are orthogonal. And here, this angle is a right angle. And so this first component should be in F, which means that the probability that it is in F is just the angle of F. And the angle will be denoted by alpha, so the solid angle. I will give a definition in a moment. So it is the solid angle of F times the solid angle of the dual phase, of the normal phase. So it is the probability that, that this projection is in F and this projection is in the normal phase. I hope it's more or less natural. And this formula is very similar to what we had for the usual intrinsic volumes, non-conic, namely there we had the volume of F times the normal angle. And this replaces, so to say, the normal angle, and this the first term replaces the volume. So here, alpha denotes the angle of a cone, and it is defined, for example, as follows, where alpha of some cone D is the probability that G is in D, where G is again standard normal or any rotational invariant vector, but not in RD, because if it would be in RD, then for such lower dimensional cones, it would give 0. Would be not nice. This is not what we mean. And that's why we take here G to be normal on the linear hull of D. So the linear hull of D is, in this case, in this case, so for example, if D is F here, in this case, it is a two-dimensional plane. Then I take in this two-dimensional plane, I take a Gaussian distribution, standard normal, and the probability that it is in D is the angle, the solid angle. So alpha do you hear this voice from? No? Okay, so I just I just
what
pressed
voice?
some button and then some voice told something.
Okay, I will check. Maybe somebody switched
So,
on.
So alpha of D is the solid angle, and we have here the products of such solid angles. And from this formula, we can derive several special cases. For example, let us assume that C is full dimensional. Then the dth conic intrinsic volume of C, it is the probability that some point is projected to a face of full dimension D, right? And C is full dimensional, so C has non-empty interior. Then it is just the angle of C. So the last conic intrinsic volume is just the solid angle. And what is the zeroth intrinsic volume? So the zeroth intrinsic volume of C is what? So on this picture, it is on this one, it is the probability that something is projected to zero. So it is the angle of the dual cone, right? It is the solid angle. It is the solid angle of the dual cone, but under what condition? So what is the condition? What is the right condition for this formula to hold? It should be the dual condition to the full dimensionality. So these two statements are in some sense dual to each other, and the dual condition of full dimensionality is which condition? So here on this picture, it's very nice because we have a point here to which we can project. But there are some cones which do not have zero as a face, which look, for example, like here. And this is the face with the smallest dimension there. So in this cone, there is no way to project something to a zero-dimensional face because there are no zero-dimensional faces. There are just one-dimensional or more. So in order for this formula to hold, C should be pointed. That is, C intersected with minus C should be zero. So this cone is not pointed, because here we have this line, both in C and in minus C. It passes through the origin. The origin is C, of course. And maybe another remark. What is the kth volume of the C dual? It is just the D minus kth volume of C. One can see it from the formula. And now, given the duality, we can state one more property, which is also crucial. So it's a theorem. It says the following. It says, first of all, that for every cone C, the conic intrinsic volumes form a probability distribution. We have already saw this for every cone C. But there is also another relation. It is called the Gauss-Bonnet relation because it is related to the Gauss-Bonnet theorem. And it says that the alternating sum of the conic intrinsic volumes is zero. So the sum from 0 to D over minus 1 to the power k of C is zero. But unfortunately, there is one exception here, which we have already seen. So there is one sort of cones for which this doesn't hold, and we have already seen them. What which cones this definitely fails. Well, there are some cones for which just one VK is 1 and all the others are 0. I see somebody is. Okay, so.
Yeah, somebody has written the right answer.
The right answer, okay, but I don't see them, unfortunately. Okay, but the answer
please,
is.
Please just talk, friends, not write, talk. It's more convenient.
Yeah, I think that for linear space, it does not work. For linear space, the distribution is a Dirac distribution. So it cannot work.
Exactly. So for every cone C.
And by the way, I have just an additional question. I wrote it also on the chat, but the previous actually, the previous figure you did just a bit before, I didn't fully understand.
Okay,
the
one
you drew a few minutes ago.
So which one? This one?
Just before, a bit before. No, yes, the one with normal face.
Yeah.
Yes, above. Yes, this one.
This one with normal face?
The one with normal face and X1, yeah.
Okay, so assume we are in dimension 4 and we have a cone which is not shown here.
We are in dimension 4, right?
Right, in dimension 4. So I forgot to write 4 here. And this is a two-dimensional face. This angle is a two-dimensional face, right? So the normal face is also two-dimensional. It is some angle which is orthogonal to that one. So now we have two-dimensional planes, the linear hull of this F and the linear hull of that one, which are orthogonal to each other. And now a point X, the claim is that a point X is projected to the interior, projected under the metric projection to the interior of the face F, if and only if, well, its projection to, let's say we have here R2 and we have here another one orthogonal to it. And I can project X to this R2 and to this R2 orthogonally, right? And the claim is that X, the metric projection of X to the cone C is in the face F, if and only if X1 is in F and X2 is in the normal face, where X1, X2 are, so to say, coordinates of this X. The first coordinate is in this R2 and the second one is in this R2. Is it okay?
Yeah, actually, no, it's perfectly clear. Actually, I didn't understood that it was a figure in R4. So for me, it was strange. I was thinking it was a figure in R2.
Okay, so this one is in R2. And this one is in R4. Now, the theorem says that the alternating sum of the conic intrinsic volumes is 0 with the only exception of linear spaces. Just the idea of proof. Well, the first relation just follows from definition, but one can also do the following. One can write the following relation for functions. The sum over all faces of C, so this is a sum over all faces of all dimensions here, of the indicator function of the relative interior of F orthogonal sum the normal face of F is 1. Just look at, say, this picture. If I take F, this one, and take the orthogonal sum, then I get this, right? If I take this one-dimensional F and orthogonal sum with the normal face, I get this. Then I can get this, and I can get this, and together it is the whole space. So the whole space can be decomposed in such direct products, and the sum of the indicator functions is 1. It's more or less evident from the definition. So this is approximately trivial. But the other relation is non-trivial, and it says the following. So there is a brother of this relation. If we take the face F, now without relative interior, and if we subtract NC of N of FC, which means that now we take not this one, but we reflect it around. We reflect it with respect to F and take it on the other side, and we do it in the alternating way with -1 to the power dimension f. Then the claim is that this is everywhere 0. This is non-trivial relation. I will not prove it, but now what is the how to derive our properties using these relations? So it's certain combinatorial relation for every cone. And now how to derive the properties of the conic intrinsic volumes given these relations? Well, we just have to integrate them with respect to the Gauss method. So integrate them. These are relations between functions. We can multiply them with the Gauss method and integrate. Integrate with respect to the Gauss measure. And now let us introduce the notion we are really interested in. So it is the notion of Grassmann angles of cones. And this notion will have applications in computing various functionals related to random polytopes. So this is really important. Grassmann angles of cones introduced by Grünbaum. So they are defined as follows. Let C be a cone. Then the kth Grassmann angle of C is the probability that the intersection of C with a random uniformly distributed linear subspace of dimension d minus k is non-trivial. So here L is a uniformly distributed linear subspace of codimension k. Now, what is the motivation for this definition? The motivation is as follows. For example, say, let this be a cone. Then the usual angle of the cone is the probability that a random uniformly distributed vector is in this cone, right? But I can take the line generated by this vector. And I can ask, what is the probability that a random line intersects a cone? And now a line, or maybe a directed line, intersects a cone if and only if the direction is either in this cone or it is in the minus cone. So let me write it as an example. If C is full dimensional, which is usually the case, and C is not the whole RD, then gamma d minus 1 of C is the probability that a line, then this is a line, a random line, intersects a cone, and a random line, I can take also some direction on this line, and it intersects the cone, if and only if this direction is either in C or in minus C. So it is two times the solid angle of C. So this Grassmann angle is just the usual solid angle, and all the others are more general, so to say, generalization. We take random subspaces and compute the probability, or look at the probabilities that they intersect this cone. And these are called Grassmann angles. So one remark, which is more or less a consequence of the definition. So for C not equal to 0, the zeroth Grassmann angle is 1, and then they are decreasing, gamma 1, and so on, greater gamma d, and they are all non-negative. So they form such a sort of tail function of some distribution, if you like, and or similar to. They are decreasing. And now the main result which we need for the Grassmann angles is a formula which allows to compute them given the conic intrinsic volumes. So this is the theorem, which is really the main part of the proofs which will be presented, or of the examples which will be presented below. So it is called the Conic-Crofton formula. Conic-Crofton And it is really crucial for what follows. And it says that if C is not linear subspace, unfortunately there is again one exception, then the probability that C intersects a d minus k dimensional linear subspace non-trivially, so gamma k of C, is given by the following sum. It is 2 times the k plus first intrinsic volume plus k plus third intrinsic volume plus and so on. Now, there are two possibilities. I can give the idea of this proof, but then we'll not have much time for all the other questions. And the proof is difficult, so I can just give only one step show only one step in this proof. Maybe I will just skip the proof if it's okay with you. Of course, it's not nice to state the most important theorem without giving any idea of the proof, but let's skip it and let us consider some examples of how this theorem can be applied. So example 1. Maybe I can give it at the end of the talk if we have time, which is due to Wendel. It's a formula of Wendel, and the problem which we want to solve is the following. Let x1, x2, and so on, xn be IID uniformly distributed points on the sphere in the d-dimensional space, or standard Gaussian, if you like. Or any rotational invariant distribution with some conditions. Okay, let us take these two for the sake of this example. We want to compute the probability that the convex hull of these points, so n points on the sphere in d dimensions chosen at random, contains 0. So something like this. This is a sphere. We take here n points, and we want to compute the probability that the convex hull contains the origin. So here it doesn't contain the origin. And it is the same as to ask what is the probability that there is no half space in which all these points are contained. Because here we can separate by a half space. But let us use this form of the question. And now this can be done as follows. So here is a solution. Well, let us look at the random event that the convex hull contains 0. What does it mean? This means by definition that there are lambda 1, lambda n coefficients greater than 0 such that their sum is 1. So a convex combination of these points which is 0. Right? So it's just the condition that there is a convex combination which is 0. Okay, now one can simplify this a little bit by doing the following thing. Suppose I have lambdas which are greater or equal than 0 such that the combination is 0, but there is no condition that the sum is 1. Then I can just divide by the sum, and after that the sum is 1. The only case in which this is not possible is if they are all 0. Then this is bad. So I can write this condition as follows. There are lambda 1, lambda n greater or equal to 0, but not all 0, such that lambda 1 x1 plus and so on lambda n xn is 0. And now there is no condition on the sum. And at this point we see that it doesn't matter whether we choose here standard Gaussian or uniform random variables, because if say they are standard Gaussian here, then I can divide each standard Gaussian random variable by its norm, and it's uniform. So if there is such a combination for Gaussians, it exists for the uniforms. So let us assume at this point that they are Gaussian, which is more convenient. Let x1 xn be standard Gaussian. And then we can do the following. We can take a vector lambda, which is lambda 1, lambda n. It is then in the positive orthant of Rn plus, but it is not 0. And we can take a matrix A, whose columns are the vectors x1, xn. So it's a matrix with these columns, xn, and it is a matrix which maps from Rn to Rd. And now the condition which we have, this one, that the combination is 0, can be written as follows. The condition takes now the form that the matrix A applied to lambda is 0, or that lambda is in the kernel of A. Right? Because what happens if I multiply A with lambda? Then we have to write lambda here as a column, and then we have to multiply it. And we see it's exactly this combination, which has to be 0. So one has to just to multiply them. So we can formulate our event, our random event, that x1, xn contains 0. This event occurs if and only if the kernel of A intersects the orthant in Rn. Now it is in Rn, and the intersection should be non-trivial. It should be non-zero, because if it is 0, then we have to put lambda equals 0, and this is not allowed here. Right, so now we translated the event we're interested in into some event in the n-dimensional space. We have here the positive orthant in the n-dimensional space, and here some linear subspace. And this linear subspace, because the matrix A is Gaussian, it's a Gaussian random matrix, this linear subspace is uniformly distributed on the Grassmannian of all n minus d dimensional subspace, because it's a matrix from Rn to Rd. So d coordinates, we have d conditions. We assume n is greater than d always. We have d conditions, so we have to subtract these d conditions, and here it is. So, and now we see it's a Grassmann angle. What we have here, the probability of this event is a Grassmann angle. So we have the probability that x1, xn, the convex half of x1, xn contains 0 is nothing but the dth Grassmann angle of the orthant Rn plus. And now for this we have a formula. So here we have our main formula, Crofton, which does the whole work here. It is 2 times, well, let me write it in this way. The sum L equals 1, 3, so all odd numbers of D plus L of R n plus. So this is the conic Crofton formula. And now we know the conic intrinsic volumes of the orthant. Some question or no? Okay, so we know the conic intrinsic volumes of the orthant. They are just binomial values of the binomial distribution. So we have here 2 divided by 2 to the power n, and then we have, well, I will write it explicitly, n over d plus 1 plus n over d plus 3 plus and so on. And at some point it stops, it becomes 0. And the last step is maybe to simplify this a little bit using the Pascal relation for the Pascal triangle. Each of these coefficients, so there are here odd numbers, right? But each of these coefficients can be written as a sum of 2 above it, and then we have the sum of all numbers, which is more nice. So it is 1 over 2 to the power n minus 1, and here we have n minus 1 d plus n minus 1 d plus 1 plus n minus 1 d plus 2 plus and so on. So essentially it is a probability that a binomial random variable is greater than d, greater or equal than d. It is it is the probability that a binomial random variable with parameters n minus 1, 1/2 is greater or equal than d. And unfortunately, we have to change the page, but one can now do the following nice observation, or let me ask you a question now. Suppose, so the probability is, I will write it down again. The probability that x1, xn contains 0 is the probability that a binomial random variable with parameters n minus 1, 1/2 is greater or equal than d. And now, given this, one can ask the following question. Suppose we choose n points uniformly on the sphere at random, independently, in the space of dimension d, which is very large, say 1 million. And the number of points is also very large. And now suppose I choose here n equals 2d points. What is the probability that the convex hull of these points contains the origin? Approximately. It's a question to all of you. I would like to know it approximately. So if you are disturbed by this -1, imagine for large n it is almost the same as n. It could be n. So what is that probability? Okay, let us draw a picture.
Is it 1/2?
It is 1/2, exactly. So
it's 1/2 now?
It is 1/2, exactly. So let us draw a picture. Here we have n. No, we have here k, I'm sorry. Or we have here k, but on this axis we have n. we have k on this axis. And here we have this term, 2n, n over k. And then we know that the central limit theorem holds, which means that we have, so this is the binomial distribution, right? And it satisfies the central limit theorem, which means that we have here a Gaussian curve and then very, very small probabilities here. So it's the visualization of this binomial distribution. And now we're interested in the probability that it is larger than d. Now, if n is equal to 2d, then this middle point, n/2, is exactly d. So in our situation, it is exactly d. So if we are in one, then it is d, and therefore the probability is 1/2 because we have to sum everything which is to the right. Right now, what happens if n is equal to 2 plus epsilon times d points? Well, then n/2, which is the middle of this distribution, the expectation, n/2 is then larger than d, right? So d is somewhere here in case 2, and we sum everything to the right, so the probability is 1. And finally, if n is equal to 2 minus epsilon times d, then we are here, and the probability, and we sum everything to the right, and it is nothing, almost nothing. So the probability is 0. So there is a phase transition here. And such phase transitions occur in such high-dimensional problems very frequently. This is the simplest one. Now, let us consider the second example. Okay, we have 20 minutes time, right? Example 2. Yes, let's do it. Let's Let's consider this example. So it is a joint work with Vlad Vysotsky and Dmitry Zakhar. And again, let x1, xn be IID standard Gaussian in RD. In fact, the same thing holds for other distributions, but now let they are Gaussian. And we consider the Gaussian random walk x with increments xi. So sk is a Gaussian random walk in RD. And let us ask, what is the probability that 0 is contained in S1 in the convex hull of this random walk? So very similar, but now the convex hull is taken of a random walk, not of IID points. Let us compute this probability. And again, we look at the event that 0 is contained in this convex hull, which means that exactly as before, that there are lambda 1, lambda n greater or equal to 0, but not all 0, such that lambda 1 s1 plus lambda n sn is 0. And now let us write this condition, which we have here as follows. S1 is x1, S2 is x1 plus x2, x3 is x1 plus x2 plus x3, plus and so on, plus lambda n, x1 plus xn, and this should be 0. And now let us regroup all these terms so that we start with x1. So x1 has to be multiplied with lambda 1. x1 is everywhere, so it has to be multiplied with lambda 1 plus lambda n, plus x2. x2 is almost everywhere. It is everywhere except for this first term. So it's x2 lambda 2 plus lambda 3 plus lambda n, and so on. And finally, xn is only in the last term. It is 0. So now we have the condition that there should be a combination of x1, x2, and so on, xn. But now the coefficients are like here. And if we denote them by y1, y2, and so on, yn, then what is the condition we have to put on these y's? So the lambdas are all non-negative, which means that the y's are decreasing, non-increasing, more precisely. So condition on y's is that they are decreasing the last one is positive because the last one is lambda n, and nothing more, right? This is equivalent to what we had. And also we have to require that not all of them are 0. So not all of them are 0. And now we can denote the set of all such tuples by W. It is called the Weyl chamber of type B. So the Weyl chamber type B denoted by Y, and it is the set of all Y in Rn such that Y1 greater Yn greater than 0. And then our condition 0 is contained in the convex hull of S1 and so on. Can be written as the condition that the kernel of A is again the matrix whose columns are x1 and so on. And the column of A, now it has to intersect this Weyl chamber, right? Because we need that the combination of x1, xn, and x2 and so on with coefficients y1 and so on is 0, which means that this y is in the kernel of A. and y is in the Weil chamber. So which means that our condition is that the kernel of A intersects the Weil chamber non-trivially. And now this is again a Grassmann angle. The probability of this is a Grassmann angle. So the probability that S1, Sn absorb 0 in their convex hull is the Grassmann angle, the Dief Grassmann angle, because kernel of A, recall kernel of A is uniformly distributed on the Grassmannian of all n minus d dimensional linear subspaces. So it is the Dief Grassmann volume of the Weil chamber. Or it can be written as 2 times, well, times the sum d plus L of V. L is odd. And now, tomorrow or later, we shall compute the intrinsic volumes of the conic intrinsic volumes of the Weil chamber, and they turn out to be some combinatorial numbers b and k divided by 2 to the power n divided by n factorial, where b and k are the coefficients in the polynomial given as follows. K from 0 to n. So take this polynomial in T, expand it, and then b and k are the coefficients. At this point, it is completely unclear why this is so. We shall prove this tomorrow. So this nice identity. Now there are 10 minutes left, and I think, or less than 10 minutes left, right? And I consider the last example, or I try at least to start it. So it is due to Affentranger and Schneider. Let P be a polytope of full dimension. So P be a polytope now in Rn. For example, a simplex, a regular simplex in the already very interesting case. And let L be a uniformly distributed subspace. Let L be a uniform linear subspace of dimension V. And let P be the projection on L. P orthogonal projection to L. So we take a polytope and we project this polytope by the map pi to L. Here the projection is some polytope here, and the question is, what is the expected number of k-dimensional faces of this projection? We shall see, I hope we shall see tomorrow why such questions are important. They have implications in various problems of linear programming, but I will not tell about this anything today. And how to compute such a term? Well, the idea is the following. First of all, given a face F, let F be a k-dimensional face of P. Then we can define the so-called tangent cone of F. P of F in the polynomial P. It is defined as follows. It is the, first of all, take some point y in the relative interior of F. So it is in F, but not in a face of small dimension. And now imagine that this is F, and this is our polytope, maybe this one, and we are somewhere here. This is y, and then we look in all possible directions. And some of these directions look inside P. These directions form a cone, and it is called the tangent cone. So it is the set of all z in Rn such that there is an epsilon, sufficiently small epsilon, such that y plus epsilon z is in P. So if epsilon is small and we add to our point y where we sit some small direction, some small vector, and if it is inside P, then it is in the tangent cone. And it is indeed a polyhedral cone. So for example, let us draw a picture. Again, I can only draw two-dimensional ones. If this is our P, so somewhere here is our polytope, and this is our F, a zero-dimensional face, then the cone is the set of all these directions. So the cone is, it is of course at the origin, so it contains the origin, and this is our tangent cone. Right? And we can also define, okay, we have almost no time, so I will just explain the idea and continue tomorrow. And now, what is the idea of the approach? Let us take some face F of P. Then this face, a k-dimensional face, then this face may survive in the projection or may not survive. So it may remain a k-dimensional face in the projection or it may not remain. And that's why we can write that the expected number of faces, of k-dimensional faces of the projection, of the projected polytope, is given by the following formula. It is the sum over all faces of the original polytope. And here I write of course, the expectation. And then we write the indicator of the event that the projected face survived. So it is a face of the projected polytope P. Right? So we take all faces of the original polytope and look whether they survive or not. And those which survive, we count them. And this number is the number of faces of the projected polytope. This is the claim. And now, what is the condition? Of course, we can now take the intersection inside the sum, if we like. And then we have the sum over all faces of fk of P of the probability that Pf survives of pi P. But now, how to write this event? How to represent this event? And this is the crucial step of this derivation. What is the condition that a face survives under projection? So imagine we project on a linear subspace L, and the direction in which we project is L orthogonal. The claim is that, let's look at this picture. So if this is a face, right, and we project somewhere in this direction, say, then it doesn't survive. If we project in this direction, it doesn't survive, right? So it survives if and only if the orthogonal complement of L does not intersect the tangent space. This is the claim. So it is the same as the probability that the tangent space of P at this face F is not intersected by the direction in which we project. So the intersection is trivial. I hope this is more or less intuitive. One has to imagine pictures, various pictures of such projections. So this is the direction in which we project in some sense. It is, of course, a linear subspace. It's not just one line. It's, in general, it's a linear subspace. And if this linear subspace does not intersect the tangent space, then the face survives. Otherwise, it is projected somehow in the interior of the polytope, and it is not a face anymore. And now we see again a Grassmann angle here. So what is that? It's exactly if L is random. Recall this L is random, and so L orthogonal is also random. It is uniform on G n minus d, and so this is the sum of the Grassmann angles of the faces of F, gamma d of T f p. So we take all faces. So in order to compute the number of faces of the projection, the expected number of the projection, we have to take all faces of f of dimension k, construct all tangent cones, and for all these tangent cones, consider this Grossman angle. And for this, we have a Crofton formula. And in the next lecture, we shall use this Crofton formula and obtain some more or less explicit expression following Affentranger and Schneider for the expected number of faces. Now, I think the time is over.